If you're making a game or any sort of complex program, you probably sooner or later will run into performance issues and ask yourself the question, how the hell do I troubleshoot this and figure out what is causing this performance issue? Well, today I'm going to explain to you how you can figure out CPU based performance issues. And this works for any kind of programming language. I'm going to teach you the general idea how to figure it out. First, in order to figure this out, we have to understand how a flame graph works. A flame graph is a way you can visualize performance and performance issues. So let's say in your game you have a mob, and the mob has something like this, an on-hit method. And when the mob gets hit, you play an animation and you play a sound. And these are two different methods. We could visualize this like this. We could have a box which is on hit, and then a box that is play anim, and a box that's play sound. One box per method. And the rows tell us what is spawning what. So on hit is spawning play animation and it's spawning play sound. And that is why these two are on a lower row than on hit. To explain this in a bit more complex terms, here we have these two methods, play animation and play sound, but now they actually do something. So both call the engine to do something, and then animation also logs something. Here is how that would look like. We have on hit calling play animation, and then play animation calls these two methods, engine animate and log something. And play sound calls this one method, engine SFX. In other words, it's a little bit like this. So the green box is all the stuff spawned by on hit. The blue box is all the stuff related to play animation, and the red box is all the stuff related to play sound. This is the first thing to understand when we want to use flame graphs. Every row is a method, and the kind of order of rows tells us which method called which other method. If we visualize this as stack traces, it shows you a kind of chronological view of which method called which other method. So this actually up here equals these three stack traces. It looks a little bit like this. We have these three paths here, and these are all individually a stack trace. So in a way, you can think of this flame graph as a way to visualize stack traces. Now, why would we do this? We can have stack traces everywhere all the time. Well, this is a graph, and so we have two dimensions at least. And so far, we've only used one dimension, which is call order. The things on top were called first, and the things on the bottom were called afterwards. But we have a second dimension. What should we use this second dimension for? Well, we can use it for time. In other words, we can use the width of the box to represent how long this method took. So the wider a box is, the more time the box took. Now, one thing that's important to understand is that the width of the box is the sum of the boxes that come below it. That makes complete sense. If we think back about how our methods look like, on hit, for example, does really nothing. It's just calling two other methods. So clearly, the runtime of on hit will be the runtime sum of these two individual methods. And that's exactly what we see here. We have one big box, which is the sum of these two small boxes. And likewise, the smaller box are the sum of what they call. If we trace this all the way, it will look something like this. We have methods calling methods, calling methods, and at some point, there's a CPU actually doing something, which is what's actually taking up all the time. So here, for example, probably have the engine having some internal method that actually plays audio and that will take actual CPU time because the audio has to be decoded by your CPU. And so that is what actually determines how long this method here takes. And because this is the only thing called by this, and this is the only thing called by this, the duration of play sound will be roughly equal to the CPU time required to run whatever this method does. And as such, the width of these boxes is the amount of CPU time required to do that thing. And so when we look at this graph later, we can see by how wide a box is, how much time it has required to run. And in general, if something requires a lot of time, of CPU time, it may be a performance issue. If you followed it until now and you're a little bit, I'm not quite sure what this dude is talking about, I don't 100% understand it, just wait 2 more minutes and then we do a practical example and it will make sense. One last thing we have to understand about flame graphs is this. If we get this flame graph, the default will be this. So let's say your mob gets hit 3 times. Then your recording will look kind of like this. You have your 3 stacks with the entire on hit stuff and then other stuff in between. That is cool and all and sometimes useful, but usually you care about something else, which is already spoiled at the bottom of the screen, I've just noticed, which is cumulative time. You want to know, in my game in general, what is the method that takes the longest to execute on the CPU, because that is the one that is taking the most CPU resources. CPU runtime equals CPU resources. So what you can do is, in the application, you can take these things which are the same and kind of put them all together. So it will take all the stacks from on hit and kind of merge them together. And then you can see cumulative time. That's how flame graph works. Now we're going to do it and you will see how to actually use this. I will show this to you for a C# project, meaning this works for Unity, this works for Godot. Doesn't matter if you're using C# or GDScript in Godot. As long as you use the Godot Mono build, you can use this method. However, pretty much any programming language has a tool that can gather this data. If you just search the internet, you will find a tool that can record this data that you need for any programming language, C++, whatever. I'm going to use here something known as .NET Trace. And what we're going to do is we're going to start the game. We're going to move the game out of the way. And we're going to do .NET Trace PS. This basically shows us what's running that it can collect. And then we do .NET Trace -p, and we take this number here because this says Godot, blah, blah, blah. So that is the game. And we just put that in here, 228778, .NET Trace collect. And you see it's now recording. And now what we're going to do is I'm just going to do random stuff in the game that used to be slow. So this spawning used to be slow. I'm going to move the mouse. Okay, I'm going to mouse over stuff. I'm going to end the turn. Cool. Now we have some data recorded. Here we just hit enter. Now we have our trace completed. If we now look, we have this file, Godot blah, 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 .NET Trace. This is the wrong format. So we're using .NET Trace convert, Godot blah, 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 and then format speed scope. I now have this speed scope file. And with that, I go to this website, speedscope.app, and I'm just going to drag and drop this file in here. So if we look, we have this thing here, something speedscope.json, but I'm actually going to use this one, v1, because I know how that looks like. And we just drag that in here, and we get our flame graph. When you open this, you might see a different view. You might see this here looking really boring and somehow wrong. You are in the wrong thread. If you hover over this thing at the top, you have all the threads that were recorded. So just choose the one that has the most time and that looks the most interesting. And that's usually the right one. This looks much more complicated than this, but it is the same exact thing. So let's take a minute and look at it. Every kind of column that you see here is something being executed. And we can click on here actually, and it will give us a trace. Remember how I said that every single one of these columns is basically like a stack trace. We can see the stack trace down here. This right now is not super useful because this is this view, which is the order in which it was recorded in. So this was where the game was somewhere in starting. This is where it spawned the level. Then I moved the mouse a bit. It's probably this. Not so super useful, right? We want this view, the cumulative view. So what we're going to do is we're going to go over here and we click left heavy. And that will do this merge that I just showed you. And it's going to take the things that take the longest and put them on the left side. And now basically what we do is we look for something that is slow and where the CPU time bar is long. So for example, here we have a thing that has taken 800 milliseconds. And now we can try and figure out what this is and find it in our code. So if we read this, we have here our method, dictatorship simulator engine pointer service try get camera array. And then there's something like viewport get camera 3D. I know exactly what this is because I created it for this video. Here we see there's a line called tree root get camera 3D that is clearly related to this, where it says get camera 3D. Well, I tell you why. This method gets called every frame because it's figuring out where the mouse cursor is on screen. This thing here basically gets a currently active camera in 3D space every frame. That is completely unnecessary because the camera doesn't change. It's always the same. So we could theoretically only do it once, but we're doing it every frame. And even something like just getting an object every frame can be expensive. So we can fix this by using this. This is just an object that I initialize once when this class starts up that is doing exactly this, and then putting it into that variable and basically caching it. If we do this one line change and then we run the same thing again, we get a different flame graph. So now the question is, have we saved time? Is our game faster now? Well, to figure this out, we need to find something to search for. So for example, we have this get camera 3D. And if I just do Control F and then paste it in, then you see it's highlighted here. So this is the old one where this took 800 milliseconds. Now we go to the new one and we paste it in and we see nothing. How can that be? Did we break something with our change? No, we didn't break something with our change. It is normal that we don't see it. And the reason is how this .NET Trace or all these sampling programs work. And so I briefly have to explain that. These programs use samples. So basically, when you record or collect, every millisecond or so, they're asking the CPU, what are you doing right now? What are you doing right now? What are you doing right now? Every line is basically one sample. And then they're storing that result. That's the entire collection. Okay, that's how it works. The thing about this is, if you have an event that is very short, and so it's between two samples, it will not show up. That's just a limitation of how this works. On the other hand, here we have an event or some code that took a very long time. As humans, we would look at this and say, okay, this took 1, 2, 3 samples. The tool will not see the 3 samples because the tool only sees it started here and it ended here. So the tool will basically record this runtime. So that is something that you have to understand when you use these tools. The time is not the actual CPU time, and it's also not showing actually everything. But this is actually good news for us because here, this took 800 milliseconds, so it showed up in 800 samples. Here, the same thing that was slow doesn't show up at all, meaning it's so short and gets called so rarely that it just never showed up, which means that we fixed this performance issue. And this is basically the core gameplay loop of this performance tuning, okay? You look at the flame graph, you find a bar that's big, then you go into your code and find that code and fix it. And then you do a new recording and check if it's fixed. You're probably asking yourself, okay, I can see now where the performance issue is, but I do not know what the performance issue is. I don't understand. I see the code, but how do I know what is slow about it? Well, let me introduce you to this. You've heard of best practices, but have you heard of worst practices? Here are some top things, okay, that you probably do wrong that will lead to slow code and how to fix them. I've taken the liberty to put them all into this one class. The first one is this. So this process here is something that runs every frame. You might think, okay, it runs every frame, so I have to be careful when it comes to performance. I'm going to be smart about this. I'm going to put an if right at the beginning, and I'm going to exit out of my method as soon as possible. I will only execute this expensive stuff down here if this is true. This sounds like a good idea, but the problem is that this itself is already an expensive query. If you run an if every frame, it adds up, okay? It's an if of a bool, okay, but it's actually unnecessary. Something you can do with Godot, and I'm sure with other engines too, is you can do this. You can set process to false, and you can basically turn this entire thing on and off for this class. So instead of having Boolean and an if, where you check every frame, should I continue or not? You just turn the entire thing off when you don't need it and on when you need it. Much faster, you don't have to do the if. Another thing is what I've just shown you with this get camera 3D. This is unnecessarily getting information from the outside world that doesn't change. You only need to get information when it has changed. If an object has not changed, don't get it, cache it, put it into some form of field. So I could here do a private camera 3D, is that a thing? Yes. Cam, right? And I initialize this to be null. And then here I could just say if cam is null, then we can do cam equal, and then all of this stuff. And basically we assign it once, and then we just reuse that every time. that is going to be much faster because we don't have to get the camera every time. Same thing with creating objects. I've not shown this in this code, but creating objects is really slow. Objects can have a lot of stuff. They have a lot of data, they have a lot of methods that they can do, and all of it needs to get initialized. Every like array that you do, the OS has to find a space in memory where it can put that array, and that takes time. So if you know, hey, I have an array, every frame I do things on that array, don't create a new array. Create the array once, and then when you're done, you just clear it. That's faster than creating a new array every single time. And it gets even worse when you have bigger objects. If we look at some Godot object, for example, let's say we want to create a label 3D. When we create a label 3D in Godot, it will create an object with all of this stuff. And it's even worse because it's inheriting from all these other things. So it's also going to create all of this stuff. It's going to create all of this stuff. It's going to create all of this stuff. It's a lot of data. So creating objects can be very expensive and take a lot of time, speaking from CPU. So again, you don't necessarily need to do that. A lot of things that you create are probably tools that the engine gives you to do something. So for example, Godot has something like surface tool, which allows you to build a mesh. If you know I need to build a mesh 1,000 times, don't create surface tool 1,000 times. Create it once and then reuse it. You store it in some global variable and you reuse it much faster. The last example I want to give you is this one. If you have a method like this, which is expensive, and I didn't go to any fancy school, so I don't know if that's the right term, but if it's completely deterministic, meaning this method only acts upon the arguments that you put into it, it does not get additional stuff from the outside, then you can cache it, meaning you know if you put the same things in, you will get the same things out. So instead of running this expensive method every frame, we could run the expensive method, put it into a cache, and then instead of running it, we can first check the cache. And if it's in the cache, we just use the result from the cache. Only if it's not in the cache do we actually run it. Because this is a stupid example. But if you have something like mesh generation or whatever, anything that's expensive, this is a very useful method to save on a lot of compute time. That's all I wanted to talk about today. I didn't have too much time today, so no fancy animations. Thanks for watching. I hope you learned something new. This is my game was Team. Bye bye.